Okay, so welcome. As I sort of tried to say in the little post about the workshop, this is for people who have a little bit of experience with Python and Jupyter notebooks and so on. If you don't, well, feel free to stick around and see what you can pick up. We are always happy to help you on the Zulip, but it might move a bit fast for you if you haven't got experience with Python before. Okay, actually, it'd be good if people can raise their hands if they have used Python before. How do I make this participant list bigger? There you go. Cool. Okay. Decent number, but not massive. That's fine. So, yeah. Good. Well, if you haven't, feel free to follow along, and hopefully it will sell you on Python being quite a powerful framework to do your work. Okay, so once you've activated the environment, you can do Jupyter Notebook and use this command in the same folder as your downloaded project. The other thing that I want to say is generally it's more fun and engaging if people ask questions as it goes. So feel free to interrupt me with questions as I go along. And if we don't get to everything, well, that's fine. At least we had fun doing it. Okay. And even now, if you have any questions at the beginning, that's also fine. So once you've started the notebook, you should see a view like this. Then you want to go to double click on tutorial, and then you want to right click on image filtering and say open with JupyText notebook. So these are not normal notebook files, they're JupyText files. So that's why you need to open it this way and not just double click it. Okay, so right click, open with JupyText notebook. And that gets us to image filtering. And now I can't move the tab for reasons unknown. That's fine. Okay, so I'm going to increase the font for people with smaller monitors and get moving. Okay, so image filtering is like the very fundamental operation. You can use it to denoise images. You can use it to find edges in images, find bright spots, all kinds of things. So it's an image processing step or even an image pre-processing step. And a lot of the steps involved are the basis for all of the deep neural networks that you are hearing so much about. So it's good to learn the basics and understand what the networks are doing. And we'll have a little exercise at the end that does that. Yeah, for those that don't know, this is a Jupyter notebook. So you can interleave code with text. And I will be saying most of these things, but it's there for you to read afterwards if you need it. So first thing we're going to do is import two libraries that we're going to use, matplotlib, pyplot, and NumPy, which is like the basis of numerical computing in Python. So the first thing we're going to talk about is local filtering, local linear filtering, which the local means that the value of a pixel is adjusted based on the values in its surrounding neighborhood. So these surrounding elements are either just a square, or they can be weighted based on a footprint, which is also called a structuring element or a kernel, depending on the context. But we're going to go really back to basics. We're not even going to look at pixels. We're going to look at a single one-dimensional signal like this. So this is just a step signal. There's 0 for half the signal, then it switches to 1. Okay, so very simple. But most signals in the real world aren't perfect. They have noise in them. So we're going to make it a bit more interesting and add some noise. So this is our noisy signal. So you can see it's still got that step centered on 0, centered on 1 with a step in the middle. But the values are a lot more noisy. Okay, so when you have a noisy signal, the first thing you want to do is remove the noise. And one normal way is to take a running average. So you average pixels that are next to each other together. So the way to do that with NumPy is to take two arrays and you add them together and divide by 2. So this is every pixel except for the last one, and then every pixel except for the first one. So it's the same signal shifted by 1 pixel, and then you just put them next to each other, add them together, and divide by 2. So that's what this does. And you can see that you get a smoother signal than the original, but not by a lot, right? So it's just slightly smoother. So if you want to do more smoothing, then you want to catch more pixels. So you can do the same thing with 3. So this is everything except for the last 2 pixels, everything but the first and the last, and everything but the first 2 pixels. So again, we're just taking a signal and then we're shifting it by 1, and then we're placing them all together, adding them together and dividing by 3. And now we can see that we get even more smoothing. There's a little bit of a leftward shift, which we'll talk about, but this is what a running mean. But you can see that it's kind of cumbersome. If we wanted to do a running mean of 11 elements, this would take a lot of writing, and it wouldn't be nice. To do that, we're going to define what we call a convolution or a cross correlation. There's some slight technical differences, but we're not going to worry about them so far. So what does a convolution mean? What we want to do is, instead of taking the whole signal and shifting it, we're going to take a little footprint or kernel that contains some weights, and then we're going to put that at every position in our signal. And then we're going to multiply the weights by the values in the signal, and then sum them all together. It's a little bit like a matrix multiplication, if you know some linear algebra. So if you want to take the average of 3 points, then you can define the array 1/3, 1/3, 1/3. And when you put that at a position in the pixel, you take 1/3 of this value, 1/3 of the next value, and 1/3 of the next value, sum them together, and you get the average of the 3 values. But the difference is, if we have this function, then we can generalize it to any size, and it will be just as easy to do. So we call this a kernel. We call the mean kernel of size 3 is an array of size 3 that is full of the value 1/3. And now we can do the smooth, we can say the smooth signal using a convolution of size 3 is the result of calling np.convolve on the noisy signal with the mean kernel. And we'll talk about modes in a bit. And if we do that, we can see that we get the same result as up here with the green line. And we can test that all of the values are close, whether we do it with the convolution or with our manual method. Okay, so that just verifies that this is exactly the same thing that we're doing. So there's a little widget that is going to show you what is actually happening. So this is the values. This is our original noisy signal, and the orange is the value of the mean of the 3 points that are highlighted. And we can basically march through our volume. Sorry, our volume. We're not at volumes yet. We can march through our linear one-dimensional signal. And you can see that the output of the average of these 3 points is this middle point. And as we move forward, the average changes position, but we're always getting the average of the 3 points that we're looking at. And then once we go through the whole array in this way, then we get the output signal, which is moved. Okay, so now I can just move this bar all the way over and get the signal. And again, if we now want to do a rolling average of 11 values, then it's just as easy as with 3 values. We just do an array of 11 with value 1/11, and we convolve the 2 signals, and we plot it, and now we get this much smoother signal because we're averaging more values. The only thing, the trade-off here is that you smear the point at which you change positions over a large number of values. So instead of having something that's a vertical switch, you get this gradual shift. And again, we can do the same thing as before. You can see these are the 11 values at the start, and then this is the average of those values. And you can see now, because you're taking many more values, these 2 points don't really have much weight, and the mean is close to them, all of the other values. So that's how you get more smoothing. Okay, so same thing as you can see, for example, once you pick up this value that's really high, you get a little uptick here, but it's not too big an uptick. And then you can run through the whole signal and average everything. So of course, I think you've probably noticed by now that the signal is getting shorter. So that's what this mode equals valid means. You know, when you get to the edge of the signal, if you're taking 11 values, you can't go past the edge, so you get a signal, a smooth signal that is reduced by 10 in size. And there's ways around that. So this is just a demonstration. So one way around it is to say, do the mode equals same, and then your signal will get padded on either side. But that has its own disadvantages, because you can see here at the end with the, so with mode equals valid, you can see that the 11 size pixel is getting shorter than the 3 size smoothing. But if you add padding, then you can see at the end, you get this steep drop off. And that's because it's padding the signal with zeros. So you can see that happening again here. So you've padded the start with zeros, and now the output signal is in the center, which is nice. So now your output signal is going to have the exact same length as your input signal. And as you move along, now you're, only taking values from your real measured signal. But as you get towards the end, let's see what happens here. Now you start adding zeros to your padding, and you can see obviously your average gets a big drop off at the end. Okay. So here's your first exercise. You want to go look at the documentation for SciPy and the image.convolve, and look at the different modes that offers. So they're different from the modes of np.convolve. And there might be something that solves the issue here. So I'm just going to give, let's say, 2 minutes. So 22 past, we'll start. Because this is all very compressed. So it's just a quick interactive thing. So I'm going to sort of drop off for 2 minutes. Feel free to ask questions in the chat or raise your hands, and then we'll go through the solution together. Okay, so look up the documentation. So this is, what am I doing? Hands. Sorry, was on the Zoom. So SciPy and the image involved. Find the documentation. Okay, so here's convolve, and we see that there's a mode. And we see that by default it's reflect, so that's already different from the modes that we saw before. We've got this really nice explanation of what everything is, you can see that reflect will take the values at the edge of the array and reflect them. Constant will put a constant on either array. So this is equivalent to what we were doing with valid for constant value 0. And nearest will take the edge value. So I think this is the idea that Ehud mentioned. Take the edge value and then repeat it over the edge. And mirror is very similar to reflect. It just skips the final value. So basically, the default mode of reflect is close to what we want. The nice advantage over of reflect over nearest is that it keeps the noise distribution of your signal, right? So if you have a noisy signal, it'll be noisy on the other side, whereas this will change the standard deviation. So for some filters, that might be important. In our case, maybe a little bit important, I don't know. So we can try that here. Let's go find convolved and do a different. I'm just going to import it here because I'll just copy it. I don't want to copy the cell, I want to copy the code. Okay, hopefully that worked. So I'm just going to paste. So we can do from SciPy import the image NDI. And now we can do NDI.convolve. And mode equals reflect. And hopefully that works. Mode equals. Go ahead. I'll just rename things so that we don't overwrite variables. Okay, so you can see that basically we no longer have that steep drop off to 0. It just gets little bit drop off because the last values are low anyway. So that's one of the things that you need to worry about when you're doing filtering is like what's going on at the edges of your signal. And this goes for deep learning again. Okay, so now let's go back to the very simple signal. And now based on how I've explained convolution works, I want you to try to think about what -1, but what if we use the weights -1, 0, 1 instead of 1/3, 1/3, 1/3, what is going to be the output of convolving this kernel with this signal? If someone jumps in, I'd appreciate it. Otherwise, I will go through the explanation. Okie doke. So let me just write down. I'll just run these things and explain what's going on. Okay, so this is our original signal. And then you can see that the output of correlated is 0 before and 0 after the change, but during the change, it shoots up. Okay, so this is finding places where your signal is changing. And the way it does that is if you have, -1, 0, -1, and all three values are 0 on the left, then you get, everything times 0 and it's 0 and it becomes the output is 0. So that's what we're seeing here. And on the right, if you have -1 plus -1 times 1 plus 0 times 1 plus 1 times 1, the -1 and the 1 cancel out. So you also get 0, which is what we're seeing here. But once your kernel or footprint is straddling this edge, you get -1 times 0 plus 0 plus 1 times 1, and that becomes 1. Now you'll notice that convolved is backwards, and that's because for technical signal processing reasons that I'm not going to cover, because they're kind of confusing, convolve actually reverses the kernel. So compared to your signal. So yeah, what we're going to use from now on is correlate. And it's a little, if you look at the convolutional neural networks, they all actually do correlation instead of convolution. Yeah, so we basically have an edge finding filter, and it finds places where our signal changes. And this is really nice when you have a nice clean signal. But when you get to the noisy signal, so we're going to do the same thing with the correlation, and we're going to use this -1. But you can see that the output is way messy. So this kind of difference filter is very sensitive to noise, and you can see now that the highest peak is no longer where our signal actually changes. It's just detecting the noise changing from one position to another. So that's why we want to do the smoothing from the earlier part to find the edges. So now we can correlate the smooth signal with this difference filter and see what the output is. And you can see now that whereas before the highest signal was not our change, when you take the smooth signal, the highest peak is again back where the change was. So you have a trade-off here where you lose a little bit of precision by doing the smoothing, but you gain accuracy by smoothing out the noise. Okay, now this is a little bit of a technical aside, but it's kind of cute and interesting. And that is that cross-correlation and convolution is assortative, so you can do it in any order. So in this case, what we did was we first used the smoothing kernel, and then we used the difference kernel. You can actually correlate the smoothing kernel with the difference kernel together, and then you get a bigger kernel that does both the smoothing and the cross-correlation. So that's what we're doing here. We correlate -101 with a third. We use this mode equals full, which means it goes past the edges of the signal so that there's even, if there's only 1-to-1 overlap, that is valid. And then we get this kernel that has -1/3, -1/3, 0, 1/3, and 1/3. So it's doing the smoothing on either side of your signal, of your difference point, and then it's doing the difference together. And you can have a look and show that this actually does the exact same thing, minus, again, the size difference that we've talked about. But yeah, you can see that the output is exactly the same when you do correlation with first by the smoothing, then by the difference, and correlation by the smoothing difference filter. Okay, so the last thing we're going to do before moving on to images is talk about the Gaussian filter. So one of the issues with the smoothing filters that we've done, which is the rolling mean, is that you can have, whenever you have step changes in your function or other kinds of changes, if you're doing a mean kernel, then a value that's very far away from your value that you're smoothing over can have a very large influence. So, say you're going along, you're smoothing, and now you want to determine the position centered, the average centered on this pixel with a kernel of size 11. The value at the edge of the kernel has exactly the same weight as the value at the middle of the kernel, and that's a bit wrong. And there's all kinds of mathematical theory why that's wrong. And that tells you that the optimal way, given some assumptions about the noise, is to use a Gaussian or bell-shaped weighting scheme along for your kernel. So things that are further away drop off in influence based on this function. Okay, so x0 is here the position, the center position of your kernel. Xi is the position along, from 0 to whatever. And then sigma is your variance. So sigma controls how wide your Gaussian kernel is. So we can make a Gaussian kernel by hand before we use the built-in functions. So here we're going to make an array that has 19 values from 0 to 18. That we find the center position, which is 19 over 2. That's not 4. That is, I think, 9, because it's integer division. Then we get an x vector, which is the xi's minus x0. So we're matching the formula here. We use sigma equals 2. Then we say the kernel is, this is that first part of the kernel, 1 over 2 pi sigma squared, times exponential of minus x. So this is, again, x here is xi minus x0, that one, squared divided by 2 sigma squared. And again, we can convolve this Gaussian kernel with the difference kernel to get a Gaussian difference kernel, which is kind of cute. So again, I'll just show it. So this is our Gaussian kernel, bell-shaped. You can see there's some artifacts because it's like a discretization of the bell curve, but you can recognize the bell curve, I hope. If you convolve that with the difference kernel, you get this thing that is a Gaussian on the left and a Gaussian on the right, but different sign. So this is like a Gaussian smoothing, Gaussian difference kernel. And if you convolve your original signal with this difference kernel, you can see that it's even a lot smoother than our mean, our running mean was. So you get some really nice smooth shapes out of it, and the peak exactly where you want it, where the signal changes. Okay, so that's all of our one-dimensional filtering. Please let me know if you have any questions. As always, just speak up. I think you can unmute yourselves. And now we're going to do the same thing, but we're going to go to 2D. So back to images, which is what you're here for. Okay, so same story. We're going to do a very simple signal to start with. So that is a bright square, which is zeros in the periphery and ones in the center. So we can use matplotlib to show this, and it just becomes a white square within a bigger black square. Okay, so this is a nice example because we can very easily look at what the input and output values are for our filtering. So we saw the mean filter in 1D, which is, 1/3, 1/3, 1/3. You can do the same thing in 2D, which is a 3 by 3 square, and the values, because there's now 9 values in this footprint, is 1 over 9 instead of 1 over 3. So this is our mean kernel. And then we can do the same thing as before. We go for every pixel, we put this little kernel on top of it. And then we multiply the weight of the kernel by the value under that position. And then we sum them all together. So now we're going to do the same thing as before, NDI.correlate the bright square with the mean kernel. And we can see the input, which is zeros and ones. And then, so let's focus on this little pixel here. So this has value 0. And if we put the kernel over this area, this 3 by 3 area, you see that it's all zeros. So it'll all be 0 times 1, 9 for all the positions except for 1 over 9. And so for this pixel, you can see that the output is 1 over 9. Now, if you move one step along, you get 7 zeros, but now you get 2 1 over 9. So you get 0.22 in this position. And so on as you move along that row. And you can do the same thing for every position in the image, including this middle one. So in the middle one, you can see that you do 1, 9, times 1 on all positions, and you get your 1 back. But everything else is a weighted average of that neighborhood. Okay, so that's very simple. Hopefully, and same as before, we can do a little demo where we walk over the image. So this is now our kernel footprint. It goes over the edge, and like before, we are padding. In this case with reflect, but because the image is black all over the edges, it would be the same as having zeros everywhere. And then we're going to change the output array here as we walk over the input array. So the first row only catches zeros, so all of these values are 0 in the output. We're still only catching zeros in this position, but now we're catching a 1, so 1 position here. And it's hard to see, but this has become a little bit brighter. And as we move right, it increases linearly in brightness and decreases again. Okay, so now you can see that it goes 1/9, 2/9, 3/9, which is a third, and then decreases again. And then here it's going up even higher. So this is now 2/9, same as here, 3/9, no, 4/9. And then this will be 6/9 because it's catching, let's go backwards. It's catching 6 pixels out of the 9 of the footprint. Okay, and you go along, and what you get is this little star shape. So just like before, it's taken our signal, which was very sharp, and it smoothed it, just, made it a little smooth splat. Okay, so hopefully that's clear what is going on with filtering and convolution. And now we're going to go from our little toy image to a real image. So look at the data.camera, which is an example data set that comes with scikit-image. So that's the image. We subsample it to take every 10th pixel just to make it easy to see what's going on in the boundaries. Okay. So you don't have to worry about this. This is just a little helper function so that I can show images side by side. So write that again. Okay, so now we're going to correlate our pixelated image with the mean kernel and show what that does. Okay, so same, I hope that was expected. You get the same image, but it's blurrier because you're taking the average, every pixel is taking the average of its neighbors, so you get a blurrier image. Okay, so edges that are sharp, which are the same as borders in our original one-dimensional signal, become smoother. And that's the same as our signal. You remember when we did a wide averaging, it became a sloping change instead of a step change. So that's the same thing here. You're smoothing out the edges in the image. And we'll talk about ways to get around that when you're trying to denoise. Okay, so just like with 3D, just like with 1D, the mean kernel is not a nice way to filter images compared to the Gaussian kernel because you can get artifacts, and we'll see what those artifacts do that, but it is the same idea as before. Pixels that are close to your Gaussian, so instead of getting a one-dimensional bell, you're going to get a 2D bell. And filters that are close to the corners, you can see you recognize more of a square here, whereas this was like now a pyramid. And we'll look at what that does for the images. And do I have the full image? I don't. Why wouldn't I have the full image? Okay, let me show you with the full size image what that looks like. What's the full size image called? Image. Okay, so we're going to do the same thing. I'm going to show Gaussian and mean filtered. So let's see, pixelated. I'm going to say image float. Smooth equals filters dot Gaussian image play. So again, 3, 109. Oh, except we need something as big as our original kernel. Let me see. Sigma equals 1 over 1 times 4 says 9. It should be 131. I think this is about equivalent. Let's have a look. Okay, so this is, let's do a 7 by 7 because it might be clearer, but actually, no, this is fine. You can see that if you do the Gaussian smoothing, you still recognize the original image. And this is quite aggressive Gaussian smoothing. If you do the mean filtering, you get these artifacts. You see these like bright boundaries here and square boundaries over here. And this is because of what I was talking about, where your footprint is actually catching the changes in brightness that are really far away from your center pixel. So this is why you would generally prefer to use a Gaussian versus a rolling average out of your image. Okay, so hopefully that's clear. Mean filter equals edge artifacts, far away influences. Okay. I wonder if this is, yeah, this is actually exactly what I wanted to do, but here we go. That's the mean. You can see these edges. That's the Gaussian. It's nice and smooth. Okay. So I just wanted to show you here what the Gaussian kernel looks like in 2D. And it's basically the same as before. You get this bell curve, but it's along 2 dimensions. I'm going to run through this exercise because we haven't done the zero notebook, but what I want to show you here is this even it's not the solution. So here we have a Gaussian kernel. It's the same as this one. I want to know what the values are along this line. And to do that, we can, the kernel is this 2-dimensional array. So I'll show that here. It's a NumPy array and kernel shape is 45, 45. So the middle is 22, 45 over 2. So we actually want the columns. In this case, it doesn't matter, but I'll do the right thing. And we can say what do I call it? Slice profile. Okay. So we want every pixel, every row, and then we want the middle column. And then we can say fig x equals vlp.subplots x.plot profile. Okay, so you can see that if I take the middle, just a profile over this Gaussian kernel, I get our familiar bell curve. And you can actually see what happens as you move away from the center to this kernel. Actually, I'm going to do, I'll just do 3. Okay, so I start plot L2. I can clean that up later. So you can see that as you move away, you still get a bell curve, but it's just scaled down. And it's scaled down because this is a symmetric across all axes. It's scaled down by precisely the value 1 away. So you can see that the peak of the second profile corresponds exactly to the position 1 away from the first profile. And the peak from the third profile corresponds to the position 2 away from the original profile. Okay, so all you're doing is you're taking a bell curve and you're scaling it as you move away from the center. This is called the filter being separable because you can look at it along any dimension and it will look the same. It's just the same values multiplied by themselves in a sense. Okay, so we saw edge filtering in 1D. Now let's have a look at edge filtering in 2 dimensions. So we now want to find the places in our image where the brightness is changing hard and changing fast. And this is very important when we get to segmentation in the next lesson. Okay, so just like before, we're going to do -1, 0, 1, but we are doing it with a 2D array instead of a 1D array. So this is a vertical edge kernel, so it'll find the vertical, whenever the value changes as we're moving vertically along the image. So this is the output of that. You can see that you get, it's probably better. Oh, I always forget how to add a color map. So the values around here are 0. This is the sky that we saw. So this is not changing very much. Then it goes from bright sky to the dark suit or coat of the person. So the values dip down. And then back here, it goes to the bright grass, so the values dip up. It's probably better if we do diverging color map. I think that's one. Yeah. So these are 0 values, and then they change in one direction or the other direction as you go from dark to bright or bright to dark. Any questions about that? I hope that made sense. I'm going to assume yes. So the next exercise, I'll just wait again a couple of minutes because we are trying to get by a lot of material, but actually we're doing okay for time. So wait till about 5:57 and see if you guys can find the horizontal kernel, so find the horizontal edges, and then the magnitude of the gradient, which is defined by this formula. So yeah, I'll just pause until then and then come back. And as always, feel free to jump in and ask questions, or either here or in the chat. All right. I don't want to shout out their answer. Take that as a no. Okay. So for the vertical kernel, the shape was 3, 1, and it was, -1. So 3 rows, 1 column, and it was -1, 0, 1. So to do the horizontal kernel, we want the other way around. So we want 1 row, 3 columns. There's 2 ways to do it. One is manual, so you can say horizontal kernel 1 minus 1, 0, 1, and put a NumPy array around that. Or I kind of like this trick, horizontal kernel. It's just the transpose of the vertical. So, and then we can do okay. So that's a horizontal kernel. I'm just going to copy the rest because I cannot be bothered typing it. To do. So this is now horizontal. And then this is horizontal. This is okay, and so you can see that this is a little bit different. I'm going to do instead, and I'll leave it. I'll just look at them up above. So this is now where it's changing from the sky to the hair, for example. And you can see that it's vertical, but here it's horizontal, it's changing from the sky to the hair and then from the hair to the sky. So it's going along the horizontal axis. And now we're getting into nonlinear kernels. So in order to get some kind of indication of the edges in any direction, we can do something like the hypotenuse of the two edges. This is the vertical direction, and this is the horizontal, or vice versa, depends how you want to define x and y. So we take the squared, so negative changes and positive changes are both become very positive. Sum them together and take the square root, and then you will get an edge. If there's an edge in any direction, you will find it. So for example, in this case, this is like the vertical bit of the coat. Because it's vertical, there's no edge found here at all, but there is an edge between the coat and the grass. It's just a horizontal edge, so we can get the best of both worlds by summing them together. So I can say magnitude is equal to np dot square root, and then we do the gradient vertical squared plus gradient horizontal squared, and then we do plots show magnitude. I'm going to say CMAP is magma for prettiness. Okay, so this is now the gradient magnitude. Whether or not you have an edge in one direction or another, you get an edge here. Okay, so these are all the places in the image where the brightness is changing. So just like before, we we defined our difference kernel, we defined our Gaussian kernel, but then we defined our mean kernel, but then there's kernels that are very common and pre-existing called, so there was the Gaussian kernel. For edge filters, there's other common kernels called the Sobel edge filter. So this is the simplest. And what this is doing is you can click through for the documentation. You can see it's very similar to before in that you have the positive, 0, negative values, but also you have a bit of smoothing. So the Sobel filter is finding edges that are continued along the orthogonal direction. Okay, so if you only had an edge for one pixel row value, then it's not enough to give you a high value for the Sobel filter. You need the edge to be continued. So it's the same idea for the horizontal Sobel, but along the other axis. And if you do Sobel by itself, then it's the magnitude exactly how we've just defined the magnitude. Okay, so we can do the same thing as before. So this is finding all the edges of the square. And this is finding all the edges of the person. Okay, so you can see that this is quite similar to what we found before. It's just a bit less noisy because the Sobel filtering does a bit of smoothing. And again, we can do smoothing before we do the edge finding, and then the edges themselves will be a bit more smooth. Okay, so things that are only a little bit of an edge don't register here. You only see the very bright edges, which is the person being separated from the background. Okay, so for the last bit, this is normally like quite a long exercise. I'm gonna skip it because there's not that many people experienced with Python here. So sorry, by skip it, I mean I'm just gonna do it myself, and then you guys can go and review it in your own time. So I kept saying that filters, are, convolutional filters are what's at the root of a neural network. And so here we're going to try to replicate that using scikit-learn. So, we've seen the Gaussian filter, we've seen the Stobel filter. These are all little footprints that humans, came up with. They figured out what the values should be that go into these little boxes. The difference with the convolutional neural network is that you have all of these convolutions, you have a battery of them, and then you have a desired output. So you have an image that you want to predict, or a value that you want to predict from the image. And then you use machine learning to find the optimal weights in your footprint to produce the output that you want. And the smallest version of a neural network is a single neuron, which is called logistic regression. So all it's doing is it's doing the weights, multiply it by the position, and then it's got a little nonlinearity so that the output is between 0 and 1, or -1 and 1 rather. So we're going to try to learn the output of the Stobel filter. So this is the target is either 0 or 1, and it is the horizontal filter of the image thresholded by the value 0.07. So we're going to show, so this is the image, and then this is the output that we're trying to learn. So we're trying to come up with a little neural network that learns these, that for this position, there should be a very bright value, and for every other position, there should not be a value. So scikit-learn doesn't know anything about convolutions. Well, that might have changed. When this tutorial was first scikit-learn conceived, was scikit-learn didn't know anything about convolutions, but it knows about image patches, right? So if you've done any machine learning at all, you know that machine learning algorithms, generally expect a matrix, and the values, there should be number of samples rows. So these are all of your independent samples that you're trying to learn from, and then number of features columns. So every sample has a bunch of features, and you're trying to predict the output of that sample based on those features. So we need to convert our image patches, the little 3x3 image patches that we saw before, to feature vectors, which are of length 9. And scikit-image has a really cute function to do that, which is called view as windows. Okay, so we're going to do that. Do I pad? I'm not going to pad. Okay, so one of the things is that, what's the best way to do this? Maybe I don't need to pad. I've always taken the middle, but I think, let me see what target. Oh, that's right. Sorry. I know. Yeah. So view as windows will take every possible patch from the image and return it as an array. But just like we were having problems with the convolutions before where the signal was shorter, it can't go past the edge. So we have two options. One is we trim the values of the target to ignore the edges, or we pad this image manually, and then we take the center, which is the original image. So I'm just going to take a subsample of the target. Okay, so let's have a look at what the output looks like. So window equals sk input. And now we say Windows is equal to util.view as Windows. And the value is the image. Now Windows. Oh, window shape, sorry. And we want windows of shape 3 by 3. That makes sense. Okay, so again, because we don't have the original images of shape 512, so I probably should have said that. 512 by 512. Now for every position that is not along the edges, so that's 510 by 510 square in the middle, we have a 3 by 3 patch. So this is now 510 by 510, and then a 3 by 3 patch at every one of those positions. So again, we want to turn those into 9 by 9 features, and we want to have every patch be a single sample. So we can do that by using numpy.reshape. So we can say x is equal to np.reshape windows. And now we'd reshape that to 510 by 510 and 3 by 3. Shape. So now we have 260,000 samples, more or less, that we want to learn from. And each of those samples has 9 features. And the thing that we want to learn is the output from this value, but again, only for the center. So to do that, we say, what's the target? I think we called it. Target 1, 2 minus 1, 1, 2 minus 1. And then we want to reshape that. So let's just say 2, 6, 0, 100. Okay, so now we have something that scikit-learn understands. We have a bunch of samples with features and a target that we want to learn, and we can make that model. So from sklearn bring our model, import acoustic regression. That is not happy with the autocomplete for reasons that I don't know. Oh dear. Okay, that worked. So we make a new one. So model is equal to acoustic regression solver equals linear. And now we can do model.fit x, y. So this is, if you've ever used scikit-learn, this is very standard. If you haven't, well, you can go learn about it later. It's a very good library. Okay. Does this have, no, it doesn't have anything useful. And now this has a little coef array that is in there. So let's go have a look at what the coefficients are that it's learned. So this is very hard to look at, but you remember that, you know, the coefficients, these are the things that are multiplied by your features. So the coefficients actually correspond to that 9 values long features. So we can reshape them to be 3 by 3, which is the original patch. So we can now look at np.reshape model.coef and 3 by 3. And this is looking a bit easier to make sense of. I still wish NumPy would not print with explanation notation, but the -1 means this is 0.4. So this is -0.4, -0.8, -0.4. These are much smaller values, so we can ignore them. And this is 0.4, 0.8, 0.4. We can multiply by 10. Let's see what happens if we do that. No, it's still useless. But you can see that it corresponds a little bit to the Sobel values. So in that it is, you know, up to some constant, it is -4, -1, -2, -1. 0, 0, 0, 1, 2, 1. So that's the same as the original Sobel weights that we looked at, which is just showing you how neural networks work in the sense of, you have a convolution that you run over your data, and you have a target output, and then you learn that output. So in this case, the target output was the output of the Sobel filter, and we sort of recovered those weights based on that output. So hopefully that gives you a little bit more insight into what the deep learning algorithms are doing. Yeah, and you can I know that probably went a bit fast, but you can review what this is doing a bit later, since you have the notebooks. So the last thing that I want to do in this lesson is talk about nonlinear filters, which are filters where the function, you've got your footprint, and then the function that you apply to those values, before we were multiplying and summing, can be something more complicated. So one of them is the median filter, where instead of taking the mean of the values, we take the median. So that's not a linear function, but it has some very nice properties. So you can see that the Gaussian smooths the image and it blurs the edges. Because the median will also change dramatically when you move across from a light to a dark place, it preserves the edges. So median filter is edge preserving. It still smooths the image and removes a lot of the noise, but it keeps the edges. So it's usually a very nice filter if you want to do some edge finding, but you want to remove some noise. Median filter is what you want to look at. And this is just another example of the same thing. So if you look at a mean filter and a median filter, the median will give you some very nice edges in your data. And there's further reading here if you want to learn more about filtering. So I think we should probably take a short break. I'm going to say 10 minutes is a good break. So I'm going to still be available if you have questions about any of this, but otherwise we'll reconvene at 25 past. And yeah, so get up, stretch your legs, come back in 10 minutes. Hey, I hope you stretch your legs. If you haven't, sorry, Zoe, it can take a while. Conda is very annoying. Yeah, basically, I think the alternative is to install NumPy, but if you haven't got experience with that, I don't think that you want to get that done in the next half hour. So feel free to give that a go later. And then I'm going to put a link in the chat, napari.zulipchat.com. So that's the Napari chat room. I highly encourage everyone to join it, hang out, and use the general or random channels to ask questions about environments. You'll find some helpful guides there. Okay, so let's close this notebook and go now to segmentation and measuring. So this will, again, probably go pretty fast. As you know, this is being recorded, so hopefully, if it's too fast for you, then you can catch up later as well. And as I said, I've shared the Zulip chat link on the chat, so I look forward to seeing most or all of you later on as happy scikit-image and napari users. Okay, so I actually went from microRNA expression analysis to image analysis, and when I first moved to my new lab, people were talking about registration segmentation. I had no idea what any of it meant. So I always start this by defining what segmentation is, and segmenting is dividing an image into 2 or more regions of interest. So you've seen that done in Photoshop, where you select a bit of the image and then you move it across. So you're segmenting that part of the image out from the rest of the image. If you've seen Terminator is segmenting this little human here in the middle of the frame out of the rest of the background. Okay, so segmentation is really, I'd say, the most important part of image analysis, because we are of bioimage analysis specifically, because we're interested in finding regions in images and measuring things about objects that are in our images. And to do that, you need to
interrupt. Oh, we can't see your screen.
Oh no. Thank you for reminding me. Share. Okay, sorry. Thanks for hopping in. Okay, so I right-clicked on this and said open with GPText Notebook. Hopefully everything I said made some sense despite the lack of seeing the screen. So yeah, segmenting is finding the objects in your image. That's something that you can do with classical algorithms, and we'll see some of them today, but that's mostly to get you used to the representations of the output, because those haven't changed. These days, mostly, segmentation, especially for 2D images of cells, is pretty well solved with deep learning algorithms like CellPose and Stardust. But you still want to get to the second part of this tutorial, which is like, once you have your segmentation, what do you do with that? How do you measure things in your image? Okay, so let's get started with a really easy thing. So you don't have to worry about this code. You can look at it later. It's just from a gallery example for how to segment 2 overlapping circles. So they're both synthetic. We've written these 2 disks, and then that's your image. And what segmentations, the way they're represented in code is by NumPy arrays that have a different integer value for every position of your image. So in this case, if you look at, you can interpret that as an intensity, but it's not an intensity because the IDs, the integers are arbitrary numbers, right? A pixel value of 1 is not inherently larger than a pixel value of 2. They're just 2 different circles, or smaller actually in this case. So here you can see that the values here are 0 of the output, the values here are 1, and the values here are 2. So that's the segmentation. Scikit-image has this function called label2RGB, which will convert a segmentation to a bunch of different colors. Napari has a bunch of extra functionality. So one of them, the canvas is OpenGL, so it's much faster, interactive, and responsive than matplotlib. The canvas has layers that you can turn on and off, so you can look at things independently of each other. And it's n-dimensional, which is very important for people working in bioimages, because typically we have either volumes or time series of volumes, and so on. So to use the viewer, you use this next thing. So we make a viewer, and then we can add an image, or we can add labels, which is the term for segmentation, because every pixel is labeled with one value or another. Or you can do the wrong thing, but just as an illustration, you can add an image. You can add the labels volume as an image. So this is your segmentation, and you add it pretending it's an intensity image. Now, the first time you launch this in an environment, this will take a while. So probably should have said all that after pressing the button. But I would like you to, if you're running this, launch it and then play a little bit with the viewer. I'll demonstrate all of these things because we have slightly limited, oh God. What is happening? This worked right before this tutorial. Okay. Let's see I'm going to try restarting the kernel and see what happens. Restart and clear up sounds. I'm going to get rid of this cell because I don't think I need it. No. Oh, this is terrible. I don't know that I'm going to. Okay, what happens if I do this? Just another question. Nope. Okay, that's amazing. Kernel. Restarting clear outputs. I'm just going to fall back to my non-tutorial environment because I know that works and some things will be different, but we're just going to have to live with that. Okay. This always happens when you're teaching. All right. So this is the classic notebook. That's okay, I think. And my scikit-image is broken. All right. Well, this just goes to show to the people in the chat having issues with environments is not you. Very good. Scikit-image pointed to yes. Okay, let's try a third time. It's going to be shut down. Third time's the charm. Okay. This is just crazy. Kernel's broken. This little thing is not good. Okay. Okay, let's get out of here and try to read it. All right, here we go. Let's see if I do this because that'd be pretty terrible. Okay. All right. Fourth time's the charm. Oh, okay. I think this one I can fix. Okay. Kernel. Restart. Yes. Okay, so I think I have to restart my computer. I'm sorry, guys. It looks like my OpenGL is messed up, and I don't understand why. Because this is the environment that I use all the time, and it's seeing the same error. Close. And I cannot run this particular tutorial without napari. So I'm sorry, I'll be back, and hopefully we can speed run this thing in the time allotted. I don't know even if I can end this without. I think there is a co-host, so I can leave. All right. No, I don't want to end. I want to leave. Leave meeting. Okay. I'll be back. Sorry, guys. Okay. I don't know yet whether this is going to work. All right, sharing my screen. Move this stuff here out of the way. Okay, so can you all see my browser? I hope so. Return. Thanks. Look at this thing. Okay, increase. So we're going to and, all right. I hope everyone's got their fingers crossed because I don't know what's going on. Click open with. Working. All right, I hope you're all cheering at home. Okay, so here's napari. So you can use zoom to scroll. Scroll to zoom. You can pan with click and drag. So this is kind of like how you would get in Google Maps. That's a little bit the model for the interaction. You also have these layers. So these are the three things that we've added to the viewer in this code. So in napari.viewer, we have added an image, added some labels, and added the labels as an image. So that's what this is. You can see over here on the bottom left, this is the status bar. Sorry if it's a bit small, but if you hover over this, if you hover over here, it's 0, hover here, it's 1, hover here, it's 2. And if we hide this layer, you can see the layer underneath, which is the labels. And now it's a bit more clear that this is one label. You can see that I'm not seeing the value here, and that's because that's the wrong, it's still the invisible layer being selected. So you need to select that layer, and then you see what's underneath the cursor. So yeah, so this is value 1, this is value 2, and just to emphasize that these are arbitrary labels, you can sort of shuffle the colors, and it's just showing you arbitrary colors for each different label in the array. Okay, so that's what's going on here. And then you've got the original image unsegmented before, and that if you select here, you've got 0, you've got false and true, and they're the two values. Okay, so that's the thing. You can turn on grid mode to see all of the layers that you've made visible in the same space. The other thing that you can do is, let's go back to not grid mode, is change the opacity of the labels layer. So that's just full opacity, and that is no opacity. So every layer can be made transparent just to overlay results on each other. The last thing that I wanted to show is that one of the things that napari is good for is editing and tweaking things. So it's usually rare that your algorithms will give you exactly the result you want. So in napari, you can take a paintbrush and then sort of fiddle with the output. So let's select a different label. You can do it manually here by increasing the value. Or you can do it by selecting a label. So that picks that label, and then I can paint. Okay, so that's more or less it. And we can close this view. Okay, but we're not interested in artificial little circles. We are interested in cells. So, and again, sorry for the delay here, but we're going to speed run through this. So this is, again, some sample data from scikit-image. Cells 3D, it has, it's a Z stack with 60 planes, 2 channels, and 256 X and Y. So spacing, I suppose I'll leave the spacing. Okay, so now we're going to show, use the imshow function, which is a shortcut for creating the viewer and showing an image. And in this case, we specify that the channel axis is the first axis. So you have to remember that in Python, indexing is from 0. So it's 0, axis 1. So that's the channels. And then the 2 channels are membranes and nuclei. And NDisplay tells us to launch the viewer with 3 dimensions rather than 2 dimensions is the display function. This is our viewer. They're the 2 layers, nuclei and membranes. And you can look at it in 3D and again, zoom in and zoom out with the scrolling. And if you want to pan in 3D, it's shift, click, drag, because otherwise by default, you're rotating with the click. And you can press home to reset the view. What is the last thing that I wanted to say here? Oh, so if you can always switch from 3D view to 2D view, and then you can look at all of the slices. You get a slider for the dimension that you've lost, and you can look at all of the slices. Okay, so just like we did edge detection in 2D, we can do edge detection in 3D. So we're going to grab the channels. So this is the membranes and the nuclei, and we're just going to normalize them to 0, 1. So we divide by the maximum value. And then scikit-image filters are often n-dimensional. So we're going to use Farid, which is like a more sophisticated version of the Sobel filter. And I should not have closed the viewer now. Okay, so here's my viewer. I'll leave it there. I'll leave this here. So now we're going to add the edges. We're going to find the edges of the nuclei using the Farid filter, and we're going to add them to the image using the yellow color map. Okay, so that's our edges. They're a little hard to see, but if I turn off the nuclei, you can see that we found the edges of the nuclei and also a little bit of what's going on inside the nuclei. Okay. So if in order to find the different nuclei, we want to find the foreground and the background. So going back to this, in addition to the edges, we want to know what's nucleus, what's non-nucleus. So to do that, we're going to use thresholding, which is basically looking at the brightness distribution of the image and defining bright things as foreground and dark things as background. So median filter we saw before is a nice way to denoise. And then thresholding, how do we, once we look at the value distribution, how do we decide? There's a whole bunch of thresholding algorithms that you can find in scikit-image filters.threshold whatever. And I won't go more into how to do that automatically, but this automatically finds you a value. So actually, we'll just show what that's doing. So if I do filters threshold denoised, you just get one value, and that is our cutoff. So anything that is brighter than 0.132, we're going to call foreground. Anything that's less bright, we're going to call background. And now you can see that we've done a good job at finding nuclei, but the nuclei have all these little holes in them and stuff. So we want to get rid of them. And morphology, which means the study of shapes, is another module in scikit-image, and it lets us define things about the objects defined by the pixels. So in this case, we can remove small holes, so that'll get rid of all of these little holes. And we can remove small objects, which will get rid of all of these little single item, noise from the outside of the nuclei. So we import that, remove the holes, remove the objects, and then we add an image. So this is now the image without the holes. You can see it's much cleaner, and it's also got rid of the stuff in between the cells. Sometimes it looks like there's something in between the cells, but actually it's just connected. It's just because it's 3D. Okay. So now we can do a segmentation. We can use scikit-image measure to label. And what that does is it finds all of the objects that are contiguous, and it will give them each one individual label. So that's what we did here. And you can see that now we have a different color for every nucleus, almost. So if I look at 3D, right, you can see each nuclei is labeled differently. There's only 2 things. This one's sort of still undergoing mitosis, so it's one object. And then all of the nuclei that are touching, because we don't have enough resolution, are merged together. So these 3 are merged together, these 2 are merged together, these 2 are merged together. So we're going to do the same thing that we did for our blobs up here, which is to run a watershed. And unfortunately, we're low on time, so I'm not going to go over the watershed algorithm, only to say that what you're doing is you're placing markers in the middle of each nucleus, and then you're doing a flood. You're flooding the pixel values until you find an edge, or until you run into some other flooding. So we need to put markers, over here, over here, over here, and then start flooding, and then that will define our different nuclei. So kind of a long-standing issue in nuclear segmentation is like, how do you find the nuclei and how do you find the points? And typically, it's very hard to do automatically. And what you do for one image doesn't work for another. So here's an example. I need to change this to translucent no depth, so that the nuclei, but you can see like if we do the naive thing, which is just following what we did for the 2 perfect circles, you just get a lot of stuff. And that's because the nuclei are imperfectly spherical, and there's a lot of little, noise and local maxima within the nuclei. So it's hard to find directly the points. So the first exercise, which I'm just going to run through because we're running out of time, was to find slightly better points. And what this exercise is meant to show you is that you can fiddle around with parameters for a long time until you find exactly the points that you want. So I'm just going to try something very simple, which is the Gaussian filters. So I'm going to say smooth equals filters dot Gaussian at the nuclei. And I'm going to do a pretty big sigma because I want to, the nuclei are pretty big in pixel space. So I'm going to say sigma equals 10 and maximum points equals max. Where did I call it? Morphology or local maximum. I'll do peak local max. And points. I'll just do this thing again. So now we don't want to do non-zero. We can just do the points. And equals 3 points. And okay, and I'm going to hide these ones to see what we've got. Okay, so that's pretty good. And again, this sort of comes from like being very familiar with this example. But you can see that even then it's like not perfect, right? So we have 1 point here, 1 point here, all of these. We're missing this one. We're missing these 2. And we only have 1, and we're missing that one. So, part of the point of this exercise is that we can, in napari, we've got this points array that is automatically generated. and we can actually go in and edit what we've done and then just move on with the algorithms that we want to use. So I don't think I need this. Set point. Yeah, look, why not? Okay, I'm not going to do this though. I need to do this. This, I'm going to get rid of this later, sorry. Okay. And so here I want to say, yes, equals add. Okay, so now we're in this mode where we're adding points. They're all the points that are already there. So we just need to find the nuclei that don't have points. So there was one here. If I remember correctly, this one doesn't, these two don't have any. And then the mitotic nucleus doesn't have any. And now we can switch to 3D just to make sure this top one doesn't have any. Okay, so I think that's all the points. So kind of the point of this demo is you can get an algorithm that gets you close enough, and then using the manual editing tools in Napari, you can sort of go that final 10%. And it can be, depending on the type of data you have, it can be much faster than trying to fiddle with your algorithms to get everything exactly the same. So now we can look at what our points looks like. So pts later.data. So these are all of the ones that the algorithm found. They're integers because they're based on the pixels, but these are the ones we added. And once we have that, we can use standard scikit-image things to put a marker there and to do a watershed based on those markers, and then to add labels. So I'll do that here. Whoa. That's marker locations. That's crazy. Okay, so sorry, something's changed in NumPy, but I think we're going to be okay. Yeah. Okay, so this is now our segmentation. Let's get rid of, I don't know what we need to get rid of. That particular one has been wiped out, and I won't explain why. But these are all of the, oh, that's right. So these are all of the nuclei that don't touch the top or bottom surface. I think something along those lines. One of the things that you really can't tell very well is that the nucleus here hasn't been segmented, even though we did our best with the watershed. And I'm not sure about this one as well. That doesn't look like it was very effective. Let's have a look. Are these two colors or one color? It's the same color. So somehow, get rid of the points. I don't know why this one hasn't been separated, but never fear. So this is the next step. We basically want to finally finish correcting what the watershed hasn't done correctly. Okay, so this also, oh, sorry, I know what's going on. So this marker is points update. No, this should be the same. No, it's not points update, it's points layer.data. Okay, that's what happened. Let's get rid of this. Okay, this is better. So go back to 3D. So now these two are two different arrays. Yeah, we're good. Sorry, I was using the wrong data. But you can see that this has not perfectly segmented these two, and this either, you can see there's a bit of a overflow here. So what we're going to do is we're going to use Napari's editing tools to make this better. So the first thing what we want to do is we want to separate this nucleus. So I'm going to pick that value, and I'm going to switch to 3D mode. And first thing I'm going to do is erase the would be spacebar. Yeah. Okay, so I want to separate, I want to create a barrier between the two nuclei. So you can do that with the eraser in 3D. Is it doing anything? It should be. I think I can see changes. Oh, come on. Everything is broken in this world. It's doing something. I see the view changing. Am I? Oh, that's what's going on. It's because I had the two layers showing. Okay. All right, we're all good. We're all good. Back to eraser. There you go. Okay. Yeah, so I was deleting one layer, not the other. That makes sense. And now I can fill that. Oh, I need to see how it only did one slice because I set the edit dimensions to 2. So let's change it to 3. And now fill the 2. Okay, so that's separated that one nucleus. And we can go and do the same thing in the other one, especially now that we know what's going on. Do this. So this one, we can, again, rotate here. Separate the 2. Pick. I can pick this value and fill. I can fill this value. All right, so that's just a little bit of a preview of the kind of editing you can do in 3 dimensions in napari. And then once you've done that, you can go to measuring your values, okay? So when you're measuring nuclei, you typically don't want to measure the nuclei that are in the border because things like your the size and so on are just going to be affected. So what we're doing here is we're going to remove anything that touches the border, but they're allowed to touch the top and bottom. So that's why we're padding here. Okay, and then I kind of mentioned that if you do segmentation, you still want to measure it. So even if you don't use this classical segmentation method, you might use something like cell pose. You still will get something like the cell pose mask. And then you can use measure.region props on that mask the same way that you would here. So they're the labels that we've saved. We passed the nuclear intensity image. And here I'm just going to show most of the properties in scikit-image will let you work for 3D data. Some of them are only 2D. Everything in this thing is things that you can measure in n dimensions in scikit-image. These are 2D only, so only works if you have 2D data. I think orientation we're trying to make 3D soon. And you can also pass your own custom function if you have some function of your data that you want to measure. If some of you have used R and tidy data, there's a way to get a tidy table from region props, and that is region props table. So it's the same thing as before, but because we need to compute everything ahead of time, you need to pass in the properties that you're interested in. We're going to do these properties. This is the label ID, the position, the area, which means the volume in 3D, the mean intensity, and solidity. So that's how spherical your object is, basically. Oh, God. I'm surprised that exists, but that's fine. So now we get, for every label, the area and the intensity and the solidity. And we can now use Seaborn, which is a plotting library, to plot all of our measurements. So what we can see here is very easily that our mitotic nuclei are very separate and different from all the others, right? So this is the image intensity is much, much higher for the nuclei, and then the area is reduced because they've contracted to undergo mitosis. So that's just like a very minor example. The other thing is scikit-image by default measures things in voxels or pixels, and typically we want to measure things in cubic microns and things like that. So again, in the interest of time, I'm just going to do the exercise. But just to show you that once you have this table, then you can do very standard, pandas data analysis and tidy data analysis. So we've got the area already. To convert it to cubic microns, we just need the spacing, and we have that from before. So I think I said spacing. Yeah, so spacing, this is the array in microns per pixel. We can say voxel volume is equal to np.product of the spacing. And this is in micrometers squared cubed. And now we can say that, what's my data frame called? It's called info table. So I can add a column to info table. And I could say area micrometers cubed. Probably better to keep underscores. Is equal to info table of area. Actually, I'll call it volume anyway. Times voxel volume. And now I can say info table.head and show that we've got the volume in cubic microns of every nucleus that we've measured. Okay. This one's a cute example. I'm going to leave that as homework since we're over time already. Sorry again for the disruption, and please ask me any questions now, or otherwise I will see you on the Napari or scikit-image Zulip chats. But thank you for coming. Hope it was useful despite the disruption. And yeah, let me know. I'm happy to answer questions now. There a chat? There is a chat. Has the spacing is uneven in Z versus X and Y with volume conversion work? Sorry, I don't know what you mean by volume conversion, but this still works because the voxel size, yeah, you're still multiplying number of voxels by the voxel area, so that this works fine. But there are some algorithms that would need to be modified to work better in anisotropic data. All right, well, if there are no more questions, thank you all for coming. And just to remind everyone, so feel free to join us on the chats and on ImageSC. There's lots of helpful people in this field. So yeah, you're not alone.